Okay, so welcome to our meeting for March, and tonight's topic is galaxies and black holes in the early universe. And as you've seen, we're joined by Dr. Aayush Saxena, and he's going to be doing the main talk tonight. So just a quick run through the agenda for those that are not familiar with the routine that we've got. Get my mouse clicking. A few notices first of all, and we'll have a news item from Len Mann. Unfortunately, Len's not able to join us tonight, but he has sent in good news reporter style, a news item that on a video. So I'll do that, and hopefully that'll work all right. We haven't tried that particular aspect of playing Zoom as a video, so let's see how it goes. And then on to the main presentation with Aayush. And finally, we'll have Richard giving us a tour of the night sky with the planetarium using the planetarium software Stellarium. Just a few notices, just to remind you that we are recording it, so be aware of what you do and say, because it's going to be recorded for posterity. And encourage you to use the speaker view, which is the small icon up at the right-hand side that allows you just to see the speaker. This way you're not distracted by what everybody else is doing and having a cup of tea or whatever. And it gives you the maximum view of the screen. Then finally, about questions, you can ask questions by using the chat button at the bottom of the screen, or after the talk is finished, we'll take questions verbally and turn your videos on so we can see you then as well. Quick mention about our next meeting. So our next meeting is on Friday, the 30th of April, 2021 at 8 p.m. And it's from Izzy Pearson, and she's going to talk about a very topical subject, the evolution of planetary rovers, and particularly up to the latest one, Perseverance. Izzy's actually an astronomer and an author in her own right. She has published a book called Robots in Space, which is all about the evolution of these planetary rovers. But she's also well known for being the news editor for the BBC Sky at Night magazine, and she presents that monthly podcast, Radio Astronomy. She has a PhD in galactic astronomy, so she's well placed to talk about these topics. But her talk will cover the lunar landers in the Soviet era in the early 70s, right through to NASA's Perseverance rover on Mars. So Lunica to Perseverance, basically. And on her book at the back page, you'll notice that there's a little caption that says, "One small step for a robot, one giant leap for mankind." I thought that was quite a good take on the Neil Armstrong line when he first stepped foot on the moon. So we're going to do the news item from Len, and I'm going to play this as a video. I hope it works all right, and just let me know afterwards if there's any problems, but here we go with this.
Right, well, the news this time is about gravity, and gravity is fundamental to everything here on Earth and in the universe. Newton formulated the laws of gravity, possibly the greatest scientific discovery of all time, I might suggest. He realized that all matter was attracted to all other matter, and his laws enabled calculations of the motions of the planets, etc. And they are used to this day for calculating orbits of satellites, space probes, etc. If I don't get my hair cut soon, I think I might start looking like Newton. Yes, and then in 1915, along came Albert Einstein and came up with general relativity. He realized that gravity wasn't exactly a force, and the motion of the planets was due to the warping of space-time. An object like the sun warps the space-time around it such that the planets follow the paths they do. Then coming forward to 1970, Vera Rubin discovered that the outer stars in our galaxy were rotating around the center much faster than they should, considering the matter that we can see in the galaxy. Hence, she discovered dark matter, probably made up of weakly interactive massive particles. That's not gravity, I hear you say, but it could be. Some scientists believe that there is no dark matter. We just need to modify the laws of gravity, modified Newtonian dynamics, or MOND, as it's called. Then in 1998, as if we hadn't had enough already, a group of scientists discovered dark energy. not only is our universe expanding, but that expansion is accelerating. This is a type of gravity. It's like an anti-gravity, where distant objects seem to be repelling each other and pushing the universe apart. Actually, no one knows what dark energy is, but it is definitely related to gravity in some form or other. Whoever cracks these gravitational mysteries will get much closer to understanding the true nature of the universe. So now onto the news. An Austrian physicist named Marcus Aspelmayer has been fascinated with measuring gravity to a very small scale. For 10 years, he worked to finally devise an experiment to measure the gravitational attraction between two tiny gold balls. You can see the two balls here in his experiment, that they each weigh less than 4 grains of rice. And it was a clever experiment. There was a bar with identical balls at each end for balance, supported on a thin silica fiber suspended. And then this setup is called a torsion pendulum. And then the force they were trying to measure was 10 million times smaller than the force of a falling snowflake. Quite incredible. They moved the test mass, this one at the front here, back and forwards, getting closer and further away to the object. And they used a laser to measure the slight movement in the torsion bar as the ball got closer and further away. And in fact, they had to do it in this oscillating form because it's the only way to be able to get a measurement with all the background noise. And in fact, they did get a measurement, and they could tell that the ball was being influenced by the other one getting closer and further away, mainly because the frequency of movement was the same. It was a very difficult measurement because of all the other possible ways that the balls were being influenced. For example, if the table was being wobbled by moving the first ball, and also it was in Vienna, and the background noise in Vienna was quite significant. So they could only do the experiment in night when everything was fairly still around them. And in fact, they couldn't use Friday night and Saturday night. They were too busy. So, but they eventually got a measurement, and it was found to agree with Newton's inverse square law within 10%, which is quite incredible. Now, the scientist believes he'll be able to improve the experiment with smaller masses down by a factor, eventually by a factor of 5,000 on the current experiment. And his ultimate goal is to test the quantum nature of gravity. And that really would help us understand the true nature of the universe. And that's the news.
Well, thanks to Len for that. That's really good, and hopefully that all worked for you. Okay, so tonight's speaker, as you've already seen, is Aayush, and he's going to talk to us about galaxies and black holes in the early universe. Just a quick note about his background. He's got an MSc in astrophysics from the University College of London. That was in 2014. And then he got a PhD in astronomy and astrophysics at Leiden Observatory, the Netherlands, 2014 to 2019. And he holds some research positions, and currently he's postdoctoral researcher at UCL. But before that, he was in INAF, that's the Institution of National Physics in Italy, in Rome. And, you know, he's well placed to talk about this subject. And I believe that he spent a lot of time studying this phenomenon. And to do that, his focus of research has been on the physical properties of these very distant galaxies. And he does it by using state-of-the-art telescopes from all around the world and the data that they gather. And he's particularly interested in the high redshift or distant galaxies that are part of the early universe evolution. So that's, for example, why the Webb Space Telescope also is focusing on infrared, is to get some of those. So we're talking about in the very early stages of the formation of the galaxies. The sort of telescopes he uses are the large optical scopes, such as at Paranal in Chile, and radio telescopes as well. So that's like VLT, I believe. So without further ado, I'll hand over to Aayush, and I'll stop sharing, and hopefully he will be able to share his screen.
Okay, thank you very much, Sean, for that.
Yeah. Okay,
very nice introduction. Okay, hopefully you can see the presentation.
Yeah, that's good.
Full screen. All right. Cool. Thank you very much again, Sean. All right. Thank you very much for having me. I'm very excited to be able to talk to you about some of the work that I do myself, but more importantly, sort of a review of the field of distant stars, galaxies, and black holes in the universe, and where we are right now, and where we hope to be in the coming years with the new optical telescopes or all kinds of telescopes coming online. So as Sean said, I'm currently a postdoctoral research fellow at UCL. I was also a student here. And then after spending 1 year in sunny Italy, I somehow found my way back to my alma mater. So I'm here for now, and this gives me an opportunity to also talk to you all about my work. It's sort of a bittersweet feeling of doing this virtually, because it would have been great to be able to visit you in person as well. But having everything online makes it much easier logistically for people like me to be able to share our work. So I'm very excited that a lot of people could join today. So let me just crack on with the things that I'll talk about. And thanks to Sean's very nice introduction, I can just quickly jump into it. So the brief outline of the talk today would be, I'll start by briefly touching upon the history of the universe, the things that we know, the things that we don't know. Len's very nice presentation also touched upon some of the things that currently are huge unknowns, and I'll hopefully talk more about them. Excuse me. And then in the next part of the talk, I'll sort of put more attention into the properties of the very early stars in the first galaxies that were formed in the universe. Then I'll touch upon the properties of complementary sort of astrophysical objects that are supermassive black holes, and try and talk about how the first supermassive black holes were formed in the universe. And then I'll tie everything in together and sort of give a brief overview of where we are today with regards to the open questions surrounding these very first structures in the universe, and what the future of observations hold for these answers. And then I'll conclude my presentation by just talking about the research that we do at UCL at the moment, and a few concluding remarks. So let's crack on with the first part, which is the brief history of the universe. So this showed up briefly in the presentation earlier as well. So I'll maybe spend a few minutes trying to sort of paint a picture of the brief history of the universe in a way, and all the different components that we now know of, and all of the different unknowns as well. So if you can see my pointer, the Big Bang happens here. So this is essentially T equals 0 for an astronomer. We have no idea what happened before that. That is currently in the realm of metaphysics for sure, but also things like string theory and very complicated mathematical formalisms. But as an observational astronomer, we are more interested in everything that is observable after the Big Bang. So we know now very certainly that the Big Bang happened, and then immediately after the universe underwent a period called inflation, where the universe expanded exponentially in a very small fraction of time. We know that inflation happened because of certain observables that we can see in the cosmic microwave background, for example, that was imprinted some 375,000 years after the Big Bang. But the exact details about inflation is still currently unknown, and there are many experiments, both theoretical and observational, that are underway to try and understand the first few seconds after the Big Bang, and also the first sort of 400,000 years in the history of our universe. So then we have the cosmic microwave background that was imprinted all over the universe. And this is when the photons were decoupled from matter, essentially. And before that, the universe was just too hot, and photons and electrons and protons were all just in a huge soup, and light could not escape from the grasp of, normal man free, they imprinted a cosmic microwave background. And then the electrons and protons and neutrons were just floating freely in the universe because it's still very, very hot. So the conditions hadn't become sort of enough for these electrons and protons or even neutrons to start fusing into the primordial atoms, which are hydrogen and helium. But as time moved on, these hydrogen atoms started forming and then started forming hydrogen molecules as well. But at this point, there was no light in the universe because to emit light, you need some sort of hydrogen fusion that happens in the cores of the stars. But for roughly 400 million years, the universe was simply too hot for any stars to form because there were neutral hydrogen atoms being formed everywhere around the universe, but they were just not, the conditions weren't right for them to start fusing in the cores of stars and start emitting light. But it was only after some 400 million years after the Big Bang that gravity could overpower the heat left by the Big Bang. And then clouds of these hydrogen and helium could start collapsing into forming the first stars. And this is when the so-called cosmic dark ages came to an end, because suddenly there were light emitting sources in the universe and there was starlight everywhere. And after these first 400 million years, stars started popping up everywhere. And then with the influence of gravity, they started sort of collapsing into galactic structures. And these were not very well ordered at the time. And it took billions of years of galaxy evolution to arrive at things like our own Milky Way, where we were able to form very stable and steady spiral structures and spiral arms. And the galaxies that we see, including our own Milky Way, are effectively a result of this 13.8 billion years of evolution. And the focus of my talk today would be trying to understand the era of the universe where the dark ages came to an end and the first stars and first galaxies and even the first supermassive black holes started to form. So we know that this must have happened at this time in the history of the universe, but we still don't fully know when exactly the first stars started forming, what were their properties, how massive they were, for example, how many galaxies were there in the very early universe, and were there supermassive black holes already in place very soon after the Big Bang? So these are some of the open questions that I will try and address in my talk today. So let me go to the first part of the talk now, which is about early stars and early galaxies. So just a bit of quick recap, if you will, from Astronomy 101 of how stars are actually formed theoretically. So the first stars, well, every star in the universe goes through this phase, but the first stars that were formed in the universe were formed from clouds of purely hydrogen gas that contained traces of helium as well, because hydrogen was the only element that was synthesized in the Big Bang. Every other heavier element was subsequently made inside stars that exploded and spread all of this material around them. So we know that the first stars that were formed in the universe must have been formed from very pristine clouds of hydrogen gas. And these clouds are being attracted towards each other through gravity. And then once they come close enough, they begin to collapse under gravity. So it's a runaway collapse where a ton of hydrogen collapses into the centers of star-forming regions. And then once a lot of gas has started sort of falling in gravitationally, it clusters, and this gives rise to a star cluster that is born in the universe. And in the very early universe, we would expect that the stars that were formed were much more massive compared to the ones that we have today. And this is because if you form stars only from hydrogen, then theoretically you can form much bigger stars than, material that contains heavier elements like carbon or oxygen or nitrogen. And not all the stars that are formed in a cluster are of the same size and the same properties. They're very different colors, which actually dictates the mass of the star or vice versa. So a more massive star, which can burn hotter, will appear to be bluer, whereas the lower mass stars, which tend to be a bit cooler, appear to be redder. And this is how we can, sort of infer the properties of stars just by looking at their colors. And the other thing, as I mentioned earlier, was we know that the early stars that were formed in the universe must have been way more massive than our sun, for example. So we expect the very early stars to be of O or B type stars, which are, I'm not sure if this is to scale, but it does capture how much larger these early stars could have been. And some estimates are that they were almost 300 to 500 times more massive than the sun, which is a G-class star over here. And the larger the star is, the hotter it burns to sustain this level of mass. And it is way more energetic as well in terms of the amount of photons that it emits and the light that it emits. So we already know theoretically what to expect from these very first galaxies. And once these stars are forming from star-forming clouds or clouds of neutral hydrogen gas, at the same time, there's gravity working on larger scales as well, which is sort of attracting these fuzzy blobs of star-forming regions that are spread out gravitationally into the very first galaxies. And these galaxies that were formed in the universe were very irregular in shape. And a good example is actually a nearby dwarf irregular galaxy, which is very, very close to our own Milky Way. But since it hasn't had the full sort of evolutionary experience, it somehow appears to be very similar to a primordial galaxy. So by studying these irregular galaxies in our own Milky Way neighborhood, we can begin to understand what the first galaxies must have looked like. And this is basically a consequence of, phases of galaxy evolution. Not all galaxies are born as spirals or elliptical galaxies. Their eventual shape and their eventual structure is determined by the kind of evolution that they go through. And what we know for now is that the very early galaxies must have all been very irregular in shape because they haven't had the time to dynamically sort of arrive at their final shape and structure. And they should appear to be very fuzzy as well. So now that we know all of these things and what we can expect from the very early stars residing within the first galaxies that were formed in the universe, we can start hunting for them effectively. And the current state-of-the-art telescope that lets us do this is obviously the Hubble Space Telescope, which has been around for a while now. It was launched in 1990, but it took 3 years to actually get it working to the standards that everyone was sort of expecting because of an issue with its optics, which effectively had to be corrected using a spectacle-like lens to help it focus light better. And this wasn't until 1993 when the first sort of service mission was sent to the Hubble to actually install these adaptive corrective instruments. And the Hubble, by comparison now, it's very small, but at the time it was revolutionary. And it has a 2.5 meter diameter mirror, which doesn't sound very impressive now because we have the very large telescopes with almost 8 to 10 meter mirrors. But for a space telescope, it's actually very, very impressive. And it had a suite of instruments observing from the ultraviolet into the optical light, all the way to the infrared wavelengths. And unfortunately, Hubble will not be serviced anymore, so it's slowly sort of arriving at its end now, but it's still going strong. And actually, proposals are due for the Hubble in a few weeks. So, us astronomers can still propose to get new observations using the Hubble Space Telescope. And the final service mission was in 2009, which sort of gave it a new lease of life in a way, but it won't last forever, I'm afraid. But I will come back to this point towards the end of the talk. But what Hubble did manage to do in its almost 30-year lifetime was give us the deepest images that ever exist of the universe. And maybe some of you will be familiar with this, but there's a patch of the sky called the Hubble Ultra Deep Field, where effectively it was started as a very sort of speculative experiment where the original builders of Hubble decided to allocate a certain amount of observing time to a blank patch of the sky just north of the Ursa Major constellation. And what they wanted to do was just collect data almost every few months or so for a limited period of time, and then just keep stacking these images to try and obtain deeper and deeper images of the universe in the same patch of the sky. And what they quickly realized was that every time they got deeper images and they created a deeper stacked image, they discovered more and more galaxies. And now we're at the phase where the Hubble Ultra Deep Field has actually managed to capture a galaxy which was 13.4 billion light years away from us. And it means that it was formed within the first 400 million years of the universe's lifetime, when the universe was merely 2% of its current age. And as I said, it's exactly what you would expect it to look like. It's a fuzzy blob, very irregular, which is obviously, I mean, it is very, very far away and the mirror is quite limited, but we can detect some sort of substructure within this galaxy. And it has since been confirmed to lie at this distance. And it's actually absolutely mind-blowing that, staring into the blank field, just discovering more distant galaxies. And this is what, we can currently look at as the sort of the frontier of observing the most distant galaxies. And just to give you an idea of what staring into a blank field and going deeper and deeper in terms of sensitivity looks like, I'll play a quick video here. I hope that it works. Let me try that again. Here we go. So what it shows is the position of this Hubble Ultra Deep Field in the Northern Hemisphere sky. So it's just north of Ursa Major, and it's actually observable from where we are. And it shows you that as you get deeper and deeper images, as you become more and more sensitive in the same patch of the sky, what Hubble has found is that you keep discovering more and more galaxies. And one of these galaxies actually turned out to be the most distant galaxy currently known. And this just puts into perspective how vast the universe is and how the sheer number of galaxies that actually exist in the observable universe. And this is just the limit of Hubble, it's not a limit of the universe. So with future telescopes, we hope to be able to push this even further and peer even further back into the history of the universe. And the Hubble Ultra Deep Field is full of these types of objects, So that example that I showed you earlier was just the most distant galaxies, but Hubble has managed to discover even more galaxies like it, which are maybe not as far as the earlier one, but still very, very far away. And an example here is MAX 1149 JD1, which was confirmed to lie at a 13.3 billion light years distance from us. So it literally appears as it was 13.3 billion years ago, and is really giving us the first glimpses into the galaxies that were formed in the universe right after the Big Bang almost. And this particular galaxy has, for me personally, the advantage that we were involved in its discovery as well. It was a huge team that made the discovery, and there is stronger evidence for its distance, like its distance measurement is more robust than the previous one. But it just shows you how the power of state-of-the-art telescopes can lead to such crazy discoveries, which were probably unthinkable a couple of decades ago. And so the main reason why we want to discover more and more of such galaxies and study them in greater detail is to try and understand the exact properties of the stars that are living in these galaxies. So as I've shown you earlier, we have the theories in place that tell us what sort of stars we can expect to see in the very early universe. but it would be now great to get the first observational evidence of these phenomena in the very early universe. And a crucial component that we want to try and constrain or try and measure is how old these stars are, what sort of components they have in their cores. Are they only made up of hydrogen, or do they have helium, carbon, and oxygen already? And these sort of measurements tell us when the first stars would have actually formed in the universe, because we can then use our models to try and explain these and back model them into the very first stars that would have been formed in the universe. So this is what motivates the study of the most distant galaxies in the universe almost. But unfortunately, as I said, these galaxies are at the very limit of what the Hubble Space Telescope can do for us, at least from a space-based observatory's point of view. And in the talk, I'll come to talk about all the latest next generation telescopes that can push these studies even further and really give us pressing answers to very pressing questions. So let me now move on to the second part of the talk, which is more about the most distant supermassive black holes that are currently known in the universe. So a quick overview of, very basic black hole formation theory. So we know that black holes can form very easily from very massive stars when they arrive at the end of their life. So basically, when you, as I said, the initial stars or clusters of stars are born from clouds of hydrogen and helium gas. And then I also told you that stars can have different masses within the same sort of gas cloud. And if they're more massive, then they appear to be bluer. And if they're less massive, like our own sun, they're probably yellower or reddish. Now, depending on what the mass of the star is initially, that basically sets its course for its evolution during its lifetime. So if you're a small star like the sun, you would never end up as a black hole. You would, once you've exhausted all the hydrogen in your core, you would probably puff up like a red giant, which will then lose its outer envelope, and all you'll be left with is a planetary nebula. And then the central sort of very cool leftover will just finish its days as a dwarf star. And then nothing happens. You just sit there effectively, radiating very mildly. But if the initial mass of the star is quite high, and specifically the dividing line between this branch of evolution and the black hole or neutron star branch of evolution is set at around 8 times the mass of the sun. So if a star is 8 times more massive than the sun, then it has a very spectacular life. So it does become a red giant, but in this case, it becomes a supergiant, which doesn't just lose its outer envelope, it actually goes supernova, where there's an unstoppable collapse of all of the gas to its center, and then it's very unstable, and then it sort of undergoes a huge explosion. And this supernova explosion basically leaves behind either a neutron star or a black hole, and both of these end products in a massive stellar evolution lifetime are very massive and very dense, very condensed into a small area, where you hear these sort of trivia things like a spoonful of neutron star is probably heavier than a few Earths or something, and it's actually how dense these things can be. But in addition to just forming stars from forming black holes from stars, we also know of the existence of supermassive black holes, which are not spread around the galaxy as stellar mass black holes would be. But there's at least one supermassive black hole per galaxy. They usually sits in the galactic center and almost orchestrates the galaxy evolution and sets its shape and its structure. And these supermassive black holes are at least 1 million times the mass of the sun. So we're not just talking about 8 or 10 times the mass of the sun, but 1 million times the mass of the sun. And we have observed, or we have seen indirectly, supermassive black holes that are actually up to 10 billion times the mass of the sun, sitting in the middle of some of the most massive galaxies in the universe. Now, these are very, very puzzling objects, because they appear to be in the centers of almost every galaxy known in the universe. But we don't really have a theory of how you can form a million solar mass structure just by following this sort of stellar evolution path. We currently don't know where these beasts came from in the universe, but they seem to be everywhere. And what I'm showing here is maybe one of the most famous images from the last, I think it was last year now, which is the first ever direct image of a supermassive black hole in a nearby active galaxy called the M87. And this basically is a very, very, very tiny fraction of the scale of the entire galaxy. But this active black hole can almost outshine the entire galaxy. And we don't know where they come from, for example. So there are some competing theories in the literature about how these supermassive black hole seeds were in place right after the Big Bang or soon afterwards, and how they sort of evolved and grew into the million solar mass black holes that we see today. And the two competing theories are they either merged from many different very massive stars in the early universe, or they just born out of direct collapse of large gas clouds that instead of fragmenting into stars, they basically keep falling under their own gravity. And at the minute, there's no observational evidence that can be used to test either of these theories. And the only way we can test this is by discovering more and more supermassive black holes further and further out in the universe. And then we can, maybe compare one theory against the other and see whether the universe would have enough time for either a direct collapse of gas clouds to happen or a merger of several different stars to happen. But all we need for now is more and more statistics observationally. And we need supermassive black hole detections further and further out into the universe. And we can do that by targeting these very specific types of active supermassive black holes called quasars. And luminous quasars are actually powered by the black hole in the middle of a galaxy being very, very active. And by active, I mean it's eating up material around it. And this can be gas, dust, or even stars or star clusters. And the more material the central black hole has to actually devour in its surroundings, the more luminous it can be. And for the most luminous ones, which are called quasars, they can be up to 1,000 times brighter than the entire galaxy. So one single active supermassive black hole in the center of a galaxy can outshine all the stars in the galaxy. So these types of quasars are real beacons spread around in the universe where we can go and hunt them quite easily just because they're so bright. And this is what many groups in the world, including my own work, are actually after. And you don't need Hubble type images for these because these are much, much brighter than the early galaxies. But you do need a lot of coverage area on the sky because these things are rare. And one example of, currently the most distant quasar that we know, which is exactly a very active supermassive black hole in a very early galaxy, is J0313 minus 1806. Yeah, these names are not very exciting. Apologies about that. But what is exciting is that it has been confirmed to lie at 13 billion light years away. So imagine, imagine a million up to a billion solar mass supermassive black hole is already in place within the first sort of billion years of the universe. Or to be precise, in the first 700 million years after the Big Bang. And it's really hard to explain these sources. So there's a one-off source, you can claim that it just happens to lie in a very lucky part of the universe. But the need of the hour now is to try and detect more and more such objects and really then use them to test theories about how these supermassive black holes could have been in place so early in the universe and what the seeds of these supermassive black holes look like effectively. So as I said, by detecting hundreds or even thousands possibly in the future of these objects in the very early universe, we can start testing theories of supermassive black hole formation and determine when and how the seeds for these black holes were sown in the very early universe. And this is very crucial to try and understand the full picture of galaxy evolution, because as I mentioned, these supermassive black holes are ubiquitous. They're found in almost every galaxy, including our own Milky Way, which is the Sagittarius A star. The black hole in the Milky Way is not active, so it does not show any signs of a quasar-like behavior. But we do see evidence of active supermassive black holes all around us, up to 13 billion light years away. So this is sort of the other prong of this problem to try and understand the formation of the first structures in the very early universe. So coming back to where we are now, I showed you this diagram again, and I showed you that the area that I'll be focusing would be just after the Dark Ages. And what we saw was that distant objects in the universe can actually help trace the history or the genealogy of the galaxies, like our own Milky Way, because we want to understand where the Milky Way galaxy came from, where stars like our own sun came from, or the stars that we see in the sky. What was their evolutionary history? And where did the Sagittarius A star supermassive black hole in the center of the Milky Way, where did that come from? And to try and answer these very sort of basic questions about our own neighborhood, about our own sun, we need to trace back the history in time all the way to the very early stars, galaxies, and black holes that were formed in the universe. And our current observations take us almost to the very first structures that were formed at around 400 million years, right after the Big Bang. But we are now limited by observations. And the current open questions that we would like to answer in the coming years were: when exactly were the first stars in the universe born? How did supermassive black holes get so massive so quickly after the Big Bang? And then once we have these two things coming in place, we want to understand what effect did these supermassive black holes have on shaping the galaxies that they sit in, because they play a very important role in galaxy evolution as a whole. So these are the sort of pressing questions that keep me up at night and give me a job. So towards the end of the talk, I'll try and now paint a picture of what the future of observations, particularly for the very early universe, could be like. And the big sort of new, shiny, revolutionary, many adjectives have been used for the James Webb Space Telescope. It was supposed to be launched many years ago, but we're still waiting, and the hope is that it launches in 2021. But the point is that the James Webb Space Telescope will completely revolutionize the field of the very first galaxies that were formed in the universe, the very first black holes that were formed in the universe. Now, this is an upgrade on the Hubble Space Telescope, a much needed upgrade that has been in the works for many, many years. And what it does is basically take everything that Hubble has told us about the universe and take it the next step where we need to go. So, for example, the mirror of the James Webb is much larger than the one on the Hubble Space Telescope. And what it does crucially is it observes in the red part of the electromagnetic spectrum, crucially in the near infrared to mid infrared wavelengths. So why this is important for very distant galaxies and black holes is because of a phenomenon called the redshift. Now we know that galaxies, stars, and black holes, they emit across the wavelength range, but the average stars are most bright in the optical, and the hotter the star, the bluer it tends to shine. But with increasing distance, this increasing redshift happens, which is basically a Doppler shift in the light of the emitting object. And the more distant an object is, the more red shifted the light becomes. So light from a blue star would be shifted all the way to the infrared just because of the expansion of the universe. And this is where the Hubble basically hit its limits, because to find the most distant galaxies or the most distant black holes, we need to observe redder and redder. And Hubble didn't really go into the infrared much. The 13 billion light year galaxies sort of sit right at the infrared edge of Hubble's capabilities. But with James Webb, we will be able to, for the first time, observe directly galaxies which are even further and further away. And theoretically, we should be able to see the first galaxies that were formed in the universe, which is why the launch of the James Webb is actually very, very exciting for people particularly interested in the very early universe studies. But that's not all that's happening in the coming decade or so. So the Very Large Telescope has been the state of the art of the ground-based telescopes, and also in the Northern Hemisphere, like Keck and the Magellan Telescope. But the time has come now to take that leap from an 8 to 10 meter class telescope all the way to a 30 meter or almost a 40 meter telescope. And that is what the Extremely Large Telescope, or the ELT, that is currently under construction in Chile would be. So this is a 4 times increase in diameter, which means a 16 times increase in the collecting area of a mirror, which comes with a host of advantages in terms of both sensitivities, resolutions, and just the capability to peer further and further back into the universe. And that's on the optical side, but there are state-of-the-art radio telescopes being commissioned and built all around the world as well. And a particular example that I love dearly is the Square Kilometre Array, which is being built in both Australia and South Africa, but it's headquartered in the UK. And it's essentially a radio telescope on steroids, where instead of just having one dish that does the observations for you, it has thousands of dishes spread across entire deserts in Australia and South Africa. And they're all sort of interlinked via supercomputers. So you can effectively think of them as a large single dish that is collecting signals from the same points in the sky all at the same time. And the Square Kilometre Array is supposed to be a black hole finding machine, because active black holes emit quite loudly in the radio as well. And that is an alternative way, or almost a complementary way, of finding these very distant black holes by pointing both your optical and radio telescopes on large areas of the sky and trying to pinpoint where the radio emission in particular from these very early black holes is coming from. And this will hopefully be completed in the late 2020s, and this gives a lot of excitement for the next sort of decade or so in astronomy, of the kind of discoveries that it will actually end up making. So now I'm almost arriving at the end of my talk. And I thought it would be great to sort of sum up everything that we've learned and put it into context of the kind of things that our particular research group is doing at UCL. So I'm part of the First Light research group at UCL, which is funded by the European Research Commission. It's being headed by Professor Richard Ellis, and we're a bunch of people working on all things distant universe. We're mostly observational astronomers, so we're trying to hunt for these very early galaxies and black holes in the universe using state-of-the-art telescopes. But in addition to doing our own work, UCL in particular is very involved with a whole host of outreach activities. And I think one thing that you may have heard from Sean earlier was Astronomy on Tap, which was started by me and a couple of other postdoctoral researchers earlier last year. So our idea was to have these interactive, fun astronomy presentations, short presentations in a pub in London. So you could mix your passion for astronomy and beers at the same time, which is what we live for, basically. But that was exactly when the pandemic, and then So we unfortunately could not launch in pubs as we had planned, but we have been holding online sessions live on YouTube, and they're for free. And if you search for Astronomy on Tap London, you'll be able to find all of our previous sessions with some very, very interesting talks. So I would encourage you to go check those out. But in addition to that, we have an annual Your Universe Festival that's held at UCL, which is like a astronomy open day where you can come and chat with astronomers. There's a few exhibitions and very cool interactive installations in place as well. And then, of course, UCL has its own observatory based in Mill Hill. I'm sure many of you are aware of it and have been there as well. And this is where we spend some time training students using, which are, I mean, they're small telescopes, but they're actually very, very good quality telescopes to do a lot of cool science with. So yeah, if you have any questions about, outreach, or if you wanted to get in touch with us at UCL, please feel free to reach out. And then with that, I'll just quickly run over the conclusions, and then we can head to the questions. So I showed you that thanks to the state-of-the-art telescopes that we currently have, both in space rather, with the Hubble Space Telescope, and on the ground, like the Very Large Telescope that Sean mentioned as well, we are now discovering stars and black holes that were formed within the first billion years after the Big Bang, which has never been seen before, and it's completely revolutionizing our understanding of galaxy formation. But we are currently limited by technology, and more statistics are badly needed to try and fully understand exactly when the first stars and the black holes were formed in the universe. And answering these questions is crucial to truly understand and appreciate our own history, our own cosmic history, if you will. And these are very pressing questions that keep me involved with astronomy, at least. But the future is very, very bright with future facilities like the James Webb Space Telescope, the Extremely Large Telescope, and the Square Kilometer Array, which is a radio telescope, promise to revolutionize the field of distant galaxies and black holes. And they promise to give an unparalleled view of the early universe, something that we've never seen before. So the next 10 years or so will be very, very exciting for people like me who are interested in the properties of these early structures. And finally, the Physics and Astronomy department in UCL is leading a lot of these exciting searches for these first structures in the universe. And I am very proud and happy to be part of this. And I would say that the future for extragalactic astronomy looks very bright. So thank you all for your attention, and I'll be happy to answer questions now. Thanks.
Thanks very much for that. That was brilliant. And you can ask questions now either on the chat, or you can do it verbally if you want to unmute your microphone and turn on your video, then everybody can see you. To do that, you'll need to go back to the gallery view where you can see other people as well, to see if anybody's got any questions for us. They're all enthralled. Nobody's got any questions. I was intrigued by the fact that quasars are forming so close to the beginning of the universe. Is there an explanation for that?
Well, there isn't. Yeah, so as I said, there are a lot of competing theories to try and explain these very, very massive supermassive black holes forming so early in the universe. And we haven't been able to pick one theory over the other just because there's not enough statistics. So if you have a one-off source, then it's very easy to explain that one-off source using a one-off theory. But to truly test that formation theory, it should be able to predict how many such objects you would expect to see at that epoch of the universe. So with the examples that I showed you, a couple of sources that have been discovered at the moment, so it's not fully done and dusted. So there's competing theories. So some groups claim that it was, just a bunch of neutral gas that had a runaway collapse, and then it formed these seeds for these quasars very quickly after the Big Bang. And then there are some groups that claim that, many different clumps of massive stars must have come together, and they all have their own sort of assumptions, and they all have their own predictions as well. So my role as an observer now would be to use these sort of future telescopes to try and do things more statistically. And when we have the statistics that we need, then we will be able to compare one theory against the other. But observationally, these things exist, which is a very, very surprising find.
Right. Yeah, thanks for that. And anybody else got questions that they'd like to ask?
I see in the chat there's some questions.
Indeed there is. Sorry, I'm slacking on my job here. Can you read those yourself?
Yes, but I also see a hand up. So.
Okay, Christopher Crow. Yeah, if you unmute Christopher and talk, that's the easiest way.
Hello there. Hopefully you can hear me. Thank you very much for a fascinating talk. I'm curious about the cycles that galaxies might go through when you have black holes that become active and then they become kind of silent for a few billion years and then they become active again. Do we see the same kind of cycles in the early universe, or do we find that these early quasars are much more abundant in the early universe?
Yeah, so you're absolutely right. These active supermassive black holes do go through phases of activity. And they can have bursts where they accrete a lot of material suddenly, and then at the end of the day, the material will sort of exhaust itself. And that is when the black hole sort of turns off. But then we see examples where suddenly two galaxies emerging together, which means that more new material is being transported for this black hole to become active again. And we see this happening all around us and in the universe as well. And what the latest sort of statistical studies have shown is that the epoch when black hole activity sort of peaked was roughly 2 billion years before the current date. So around, 10 or 11 billion years after the Big Bang. So we see almost like a peak and then a complete drop off after that epoch. And that is linked to a whole bunch of other physical phenomena as well, because what we find is that when the black hole activity peaks, the merger rate of galaxies peaks as well. So it essentially tells us that when two galaxies merge, or whenever there's a lot of mergers happening in the universe, the black holes in the universe tend to be more active as well. And yeah, so as I said, this is easy to do statistically in the nearby universe in a way. But we currently don't have enough detections in the very early universe to be able to make similar claims. And that is something that we hope to do in the next 5 or 10 years, when we can start detecting hundreds or even thousands of these objects. And then we can correlate them with the properties of galaxies as well, to try and understand how the black hole activity actually is right after the Big Bang.
Great, thank you.
Stuart has a question as well. If you want to talk, Stuart.
Yeah, thanks, Sean, and thanks for inviting your neighbours Rolos to these meetings.
It's a pleasure.
No, my question is that's quite striking what you said there about the James Webb giving access to visible light from these deep objects. The visible light is going to be in the infrared. So that therefore means that what Hubble is currently detecting from these very far galaxies is deep in the blue. How far into the blue, into the ultraviolet, or even further, even bluer than that? How energetic is the light that Hubble is detecting from these most distant objects, like the one that you described, which is at the age of 2% of the universe?
Yeah, so that's actually playing very nicely into Hubble's capabilities as well, because as I mentioned, the younger the stars are in a galaxy, the bluer they tend to be. So if you were to expect very early galaxies, a lot of their radiation would be in the blue ultraviolet regime already. But because it's redshifted into the infrared, that is where the Hubble the reddest part of Hubble is what we can see in the bluest part from these galaxies. So this is why Hubble itself is actually able to detect galaxies 13.4 whatever billion light years away. But the next step needs to be made purely in terms of the wavelength coverage that we can get with the James Webb. So it's actually, yeah, I mean, Hubble wasn't designed to be, searching for these galaxies, because back in the 80s, people weren't even sure if there are, observable structures in the universe just a few billion years away from us. So yeah, it's just been one of these, discoveries that no one really planned for, but now future telescopes are being designed for these very discoveries to be made. So Hubble has been revolutionary in that. And the fact that it can capture ultraviolet radiation from the most distant galaxies in the universe is actually very, very nicely playing to its capabilities.
Maybe we can pick up some of the questions that were asked on the chat. From Stephen King, what was dark matter doing in the early universe not affected by high temperature? Any involvement in SMBH formation? And then there's a couple of more bits here, maybe Stephen will actually clarify, but how much are first stars formed due to high CDM concentrations? He's got another couple of questions here. Why does forming stars from pure H2 allow larger stars? So we can see very ancient stars near us, Methuselah's star, for example, older than the universe maybe. What can we learn from such stars? And finally, what was the radius of the universe when the CMB was formed? A lot of questions there, so I don't know if you want to go through those.
Yeah, a whole variety of questions.
I know.
So I'll try and, briefly answer all of these questions so as to not take up too much of time. So dark matter is a very interesting question, and it's also very open. Because we know that for all we know about dark matter, and I mean, as we saw in the introductory news item as well, we don't know much about dark matter. We just know that it interacts gravitationally, but we don't know how it behaves in high temperature environments, high pressure environments. And in all the simulations of galaxy formation, we basically treat dark matter as only interacting gravitationally. So to answer the question about is it affected by high temperature, we have no evidence that suggests that it is. So in all sort of formalisms for galaxy evolution and even supermassive black hole formation, it just sits there sort of offering a halo for galaxies to be formed in. And the way it impacts, say, the first stars or the first black holes is basically the way it impacts galaxy formation in general. So we know that dark matter halos do combine and they grow with time, just like galaxies and black holes grow with time. So the black hole, the dark matter that is formed in the early universe sort of lays the seeds for these early stars and early black holes to start forming in. But does it have any additional impact on black hole formation, particularly in the very early universe? We're not entirely sure because, as I said, it doesn't really correlate well with other universal properties like temperature or pressure. And I think for the last, so yeah, the question is, why does forming stars allow for larger stars? So this actually is a very complicated bit of star formation physics, because the more elements you have in a gas that is forming stars, the easier it is to dissipate heat from that sort of cloud. And the more heat you dissipate, the more sort of fragmented the cloud becomes. So if there's only hydrogen, then not a lot of heat is lost while it's collapsing into gravity. But if you have things like carbon, nitrogen, or oxygen, they can suck out a lot of heat from this collapsing cloud, which ends up fragmenting the cloud and making smaller stars. So if you have only a hydrogen gas cloud, then you can keep collapsing into larger and larger stars without breaking up, without fragmenting. So this is what helps the early stars be much more massive than their more metal-rich counterparts. I'm afraid I can't comment much on the radius of the universe when the CMB was formed because, yeah, I'll have to read the paper. It's not really my area of expertise, but I'm sure there are estimates. But we treat the universe as infinite, so I don't know what the correct answer would be. And what can we learn from stars that are very ancient? I'll have to look it up as well because I'm not particularly aware of the. So up to you on that.
Yeah, no, thanks, Aayush. I appreciate you trying to work through the list.
Okay, good for that. There's a couple of other questions. I don't know, we've probably still got time to do them. So this one is from Nigel Wright. May I ask how long the inflation period lasted?
Well, so not very long. Some estimates suggest that it was 10 to the minus 34 of a second, so 0.34 zeros of a second, which is absolutely ridiculous. But inflation at the moment is only a theoretical formalism. There are many flavors of inflation, and it predicts a whole bunch of observables that people are trying to observe in the cosmic microwave background. But the short answer is it was a very, very tiny fraction of a second. So this is some exotic physics that we haven't discovered yet, something similar to dark energy. Well, we do know that it did not last for a very long time. Very tiny.
There's a question from Bernice. It says, could you please explain a bit more about what you mean when you say that the black hole at the center of our galaxy is inactive?
Yes, so this sort of ties into the first question that we had was galaxies, the black holes in the center of galaxies go through phases of activity. And the activity depends on how much material the black hole can actually gobble up. So it needs fuel to remain active. So we know from some observations of our own Milky Way that our black hole was active in the past at some point, but it simply ran out of fuel. And at the moment, if you look at Sagittarius A star through a whole bunch of different telescopes, we don't see any signs of the black hole actively accreting material, which is why we say that the black hole in the center of our galaxy in particular is inactive. But it did have a phase when it was active. And we now know from a lot of galaxy formation theory that every galaxy must have gone through this active phase to sort of stabilize the growth and achieve the morphology that galaxies have achieved. So black hole activity is a very crucial phase in the lifetime of a galaxy.
Okay, we've got a couple more and then I think we're done. One from Kwong Man. Can you say a few words on when dark matter started influencing galaxy formation?
So dark matter is always needed to form galaxies. So it basically is a dark sort of bunch of gravity particles that we don't even know if it's a particle or whatever, but it is a dark matter halo. And within this halo is where all the stars form. So we know that because of fluctuations brought upon by the Milky Way, there are some high density regions and low density regions of dark matter distribution. And within the high density regions is where the galaxies form. And in the low density regions is where, there's empty space, which is why the universe is not just a giant galaxy full of stars everywhere, but structure is formed in, different parts of the universe. And these are set by the distribution of the early dark matter right after the Big Bang.
Good explanation. Thank you very much. And how do we determine the mass of a black hole as 1 billion times our sun with an object 13 billion light years away? That was from Pravin.
Well, with a lot of observing time. Well, yeah, so there are many ways to determine properties like black hole mass. The most common and the most easiest way to do this is by studying the velocity dispersion of material around this black hole. So we have limits on how much material, how quickly the material can move around the black hole. And that limit is set by the mass of the black hole. So this is just basically dynamics that set these limits. And using a telescope, or specifically a spectrograph, you can target emission from carbon, nitrogen, or oxygen, and then you can measure how the velocity structure is of this emission. And using that, you can put very accurate estimates on what the mass of the black hole must be to sort of sustain that level of rotation in the gas that's falling into the black hole.
Okay, so we've got two more, and finally this one is from Jared Sheldon. He says, is dark matter prevalent in earlier galaxies? Probably a difficult one to
Yeah,
answer.
for all we know, we need dark matter to form galaxies.
Okay, good. Yeah. And then do you know what causes a black hole to peak?
Well, I think you mean peak in terms of activity.
I think that's what they mean. That was from
and
Jane, or sorry, it wasn't Jane, it was probably Andrew.
Yeah, so as I mentioned, the black hole activity peaks when it has a lot of material to accrete in its surroundings. And there are many things that can trigger accretion or activity in a black hole. And merging of galaxies is the most common way that a black hole becomes active again. So if you want a black hole, so for example, if the Milky Way were to merge with Andromeda, many 100 million years after now, we may expect the black hole to become active again because some new stars have been thrown into the center of our galaxy that could be gobbled up.
And you'd be pleased to know we've reached the final question, which is from John Belling, and it's, what assumptions are made about the constants of nature, G, C, in the early universe?
Well, the constants of nature, by definition, must always remain constant. So in every theory of galaxy formation or gravity or stellar evolution, we must retain the values of these constants. You would find some theoretical physicists who try and change these constant values to explore more exotic physics and things like parallel universes where, these constants could be non-constants. But from an observational point of view, we must treat all these constants as untouchable. Okay. And all the theories and observations that we make must adhere to these constants.
Brilliant. Thank you very much, and especially for answering so many questions. Really appreciate everything. So if everyone can show their hands. Thanks again, Aayush. But next, we'd like to move on to Richard, and he's going to do a planetarium presentation for us on the night sky, upcoming night sky. So I'm going to stop sharing, and I'm going to make Richard the host for that.
Richard, how about you tell us what is there to see? And we've probably all got Stellarium on our...
Yeah, sure. Yeah, okay. No, that's fine. I was going to start off by saying that Patrick Moore, when he was confronted by a really good talk in the in a meeting or whatever, and he had to do a little bit afterwards, he would sometimes say, after the Lord Mayor's show comes the dust cart, meaning himself coming along, shoveling the stuff up. And I feel a bit that way myself. But however, one thing you have to remember is, please remember to put your clocks on tomorrow. That's pretty standard knowledge, but you'd be surprised the people that can manage to get by without knowing about that. Now, what I was going to talk about this evening was the constellation of Virgo. Now, Virgo is beneath and to the east of Leo, and it has one or two interesting features. One of which is the fact that it forms a Y shape. If you look for a star fairly low down in the sky in the southeast at the moment, you'll come across Spica. Now, many years ago, there used to be a series called UFO, which was produced by Jerry Anderson, and he one of his particular sessions, one of his programs, mentioned the fact that somebody bought a telescope and could see this star called Spicer in the field of view, and I thought, no, it's Spiker. Get it right, get it right. And incidentally, the scope had prominently on it fuller scopes. So anybody remembering old telescopes, remember fuller scopes did pretty well, and they got a bit. Anyway, the fact is that Spiker is the major star of Virgo. It's the ear of corn. What it is, she's supposed to be a goddess holding an ear of corn because she's the Mother Earth goddess. The Romans called her Astrodea, and she was the god of justice. Apparently, she got so fed up with the Earth that by their bad behaviour that she'd left and come in the sky, and that's why we have Virgo. Anyway, Spiker is very interesting because it's a very white star, very much like star in Leo, Regulus, two very similar stars, both first magnitude. But the interesting star here is not particularly Spiker, but if you go up to the middle of the wide of stars that makes up Virgo, you'll come across one, Gamma. Now, Gamma has a popular name. It's called Porrimar, and that star is a double star. It was discovered by Sir William Herschel as it being double, and that particular star alters quite rapidly. It takes 160 odd years to complete a revolution of the two stars about each other. And recently, in the years up to 2000, it got steadily closer and closer and closer until they were inseparable by all major telescopes of any size. Now, previously, when I first moved to Watford, that particular star was an easy pair to separate, as Castor was difficult. Castor was actually quite a difficult star to separate in Gemini, but now the reverse has happened over the last 50 years, and in fact, Castor is much easier to separate because the two components have moved apart considerably, and up until a few years ago, Virgo was practically impossible to separate. But I understand the separation now is much wider. It's still pretty close. It's about 2 seconds of arc across, 2 arc seconds between the two. It probably is a little bit more than that now because that was not 2016. And it makes an interesting subject for a small telescope. And one of the things that I haven't actually seen this myself, I haven't looked at it for a good few years, so I'm intending having a look to see what it's like, because it seems interesting to me. And I remember it when it was much wider. And I thought this might be an idea for a few other people to try it, but it gives you some idea of the fact that the sky is, nothing really changes much. And yet there's something that over 50 years has changed quite a lot. It's opened out, it's closed, and now it's opening out again. So it gives you a bit of a kind of glimpse that what we're actually seeing in the sky is like a single frame of a cinema film. And the only way we can maybe in our lifetime see 2 or 3 frames, but we never see much more than that. Now, when you think the moving picture is 24 frames a second, we're not seeing very much of the movement of the sky in an obvious way. But this is one thing we can see. Now, Virgo, apart from Gamma, has also a lot of galaxies. There's a Virgo field of galaxies, which is mainly contained in that bowl of the Y. There's lots of galaxies there. I won't go into them. There's a lot, and almost any telescope will show them. However, you do have a problem with the constellation Virgo. It's low down, and the problem we have with it is that when it's visible, it's in the sort of April, May, June part of the year, when we have very light skies. So Virgo, the best time to actually observe the galaxies is probably in the early morning in December, which few of us would like to do. So there is a bit of a problem with that, but people do get nice pictures, and there are a lot of fascinating galaxies, including M87 and many others. The one that's most often featured in pictures is the Sombrero. Now that, apart from the fact it's called M104, it wasn't actually discovered by Messier. In fact, it was only added to the list sometime in the mid 20th century, because there's a rough indication he could have seen it. But that is not in the Virgo cluster of galaxies. It's actually much lower down. And if you look at Spica and then you move your telescope a little bit to the west until you come to a constellation called Corvus, which is a diamond-shaped group of stars, pretty low in the sky, you will come across the Sombrero. It does actually look a little bit more like a galaxy than some of the others, because you can see the beginnings of the sort of central bulge in the middle, but it's not really that easy to see. And I'm afraid with light pollution being what it is and other things, it's really not really that easy to see from the UK, bearing in mind also that we have this constraint over the lightness of the sky in the months when Virgo is available in the evening sky. So that is a bit of a disadvantage. Now, high up, we've got the Plough, and in the east, we've got another star, Arcturus, which I've mentioned before, which is part of the constellation of Boötes. It's the brightest star, and it's the bottom part of the kite shape that marks Boötes. It's a relatively nearby star. In fact, Arcturus, Spica and Regulus are relatively close, and the thing about Arcturus is that it's actually moving over apparently a short period of time, and it was actually Edmund Halley that pointed out that Sirius and another star actually had moved since the ancients have done their catalogues and their star charts. And he was the first person really to point this out, that the stars actually were not fixed; they did actually move. So that's another interesting point that you can gain when you look at the night sky. And also, there's another thought that occurred to me. We are in an ideal part of the galaxy. You've looked at galaxies this evening, lots of and very distant ones, close ones. And the fact is that we're in a good position, because if we were in the middle of the galaxy, we will be subject to black hole problems, hard radiation, stars not living very long because there's lots going on, hot stars and stars in erratic orbits going around the center of the galaxy. It would be really like chaos. It'd be like a native from an African island suddenly being dumped in Piccadilly Circus and wondering what the hell's going on and why everybody keeps honking at him because he keeps going across them in the wrong way. So it'd be quite nasty. But where we are in the suburbs, well out, we get not only to see the center of the galaxy, we get to see other galaxies as well, because in periods when we're like autumn and spring, when we're away from the center or arm of the galaxy that's closer to the center, and the other one on winter side, we actually get to see galaxies. So we actually get a good sample from our position of things like globular clusters, center of galaxies, other galaxies, and all nebulous patches where unborn stars are being born. So we're pretty lucky, really. I think we've got a real Goldilocks planet. And one of the things that I particularly enjoyed was reading an article by Graham Merritt on the fact that life on Earth has actually done very well, considering the length of time and the hazards that we've had. And it makes you wonder about how intelligence came. We've been very lucky. With all the twists and turns, that we're still here. So I'd like to leave you with that thought anyway. And I'm sorry about it's a rather abstract talk, but I hope it's given some insight to some of the things that we were going to talk about. Okay, thank you very much.
Thank you.
Thank you for that, Richard. It was very, very informative. Brilliant. Thank you.
Thanks for soldiering on, Richard. Under difficult circumstances.
That's a good one. The thing I need to do now is describe a spiral staircase without using my hands.
Yeah. 2 cylinders, 1 cylinder inside the second cylinder.
Very good. Very good.
Yes,
somebody could do it.
That was a very good talk, and we're all learning how to communicate using Zoom. It's all new to us. Well, certainly is to me.
Yeah,